I'm Paul Knudsen. I'm one of the students who works at Mission Exploration Laboratory as the TBEX operations lead. And then Justin here is this MC9 lead.
Yep, so moving on. So MXL is a lab. We're centered on flight vehicles. So we're a little lab that's nestled in the AERO department underneath Professor Cutler. So we build space systems mainly, but our main goal is to enable old, small exploration vehicles. So whether that mean under ice vehicles in the future, turning CubeSats into potential rovers, working with drones and high altitude balloon vehicles as well. So here are depicted a bunch of vehicles that we built in the past. So we'll kind of dive into some of the ones we've been working on in the past year. And there's a picture of a high altitude balloon that we launched a couple years ago up Peach Mountain Radio Observatory in Pinckney. And so, as I just said, so we're a little lab that's nestled in the aerospace department. And so we're kind of an interesting blend of doctoral students, master's students, and undergrads. And unlike some more professional laboratories, we're very highly balanced towards using undergrads to help teach them how to build space systems and enable some of these missions and do some of the innovative research that we do. So kind of going more into that research. This is some of the past satellite missions. I'll let Paul explain some of these.
Yeah, so we were actually the first NSF mission with RAX-1. So that was kind of when the lab actually was first called the RAX lab, and then after there became more than one CubeSat, we just became the Mission Exploration Laboratory. And so we've now done 9 satellites since that first one. Our most recent one is TBEX, which we're going to talk about more later. That one's a currently active mission. But we've done all different kinds of payloads. We've done radios, we've done Earth observation, ionospheric science, and we're always learning more.
Yep, and here's some more. And so our upcoming mission, so we have a mission that's on order right now that Paul's leading, so that's the TBEX operational mission. And we should also mention that with MC9, in the past, people like NASA and JPL and SRI and Southwest Research Institute have come to us and said, hey, here's a bunch of cool, interesting science things that we want to do and payloads we want to fly on missions like Marco, on Griffix, Cadre, TBEX, etc. But we're looking into developing some teams to be able to develop some of our own payloads and science experiments and be able to generate both the science side and the spacecraft side as well.
Okay, so this is kind of our year in review. I was actually at the Falcon Heavy launch with STP-2, where we launched the 2 TBEX satellites. And I can personally attest it's one of the coolest things ever. Rocket launches are pretty rad.
Especially when your hardware is on it.
yeah. The adrenaline from both hoping it doesn't crash and the other side. Yeah, so this kind of started out with a bang with the STP-2, and then since then we have done a lot of other research. We've been working on the next satellite mission, which is MC9. We actually have been moving labs amongst a lot of other lab moving in the AERO department. We've been doing more research in orbit determination and really focusing on operations a lot, because we have a lot of spacecraft on orbit right now, and some of them have their primary missions have been completed, and so now we just have spacecraft up there that have capabilities, and so we're trying to find even new uses for that data and trying to figure out what else we can learn from it. So as an example of that, something we're working on is trying to use CubeSat data to be able to predict, use then machine learning to then predict satellite errors. And that's something we're doing with Griffix data. And then there's a couple other things we've also been working on, as you can see. But yep, it's been a busy year.
Yeah, and so I'll add one point to that, which is so in the past, I just mentioned that MXL kind of takes all these different payload providers and will build the spacecraft around their payload. But one of the cool things that we've been working on this year is doing some technology demonstrations for some of our own payloads, which is our research into space situational awareness and how to ensure that when we have some of these objects in space that we put there, that if they were to ever go down during a mission, so if they're ever to become uncontactable or go rogue, which is not so uncommon of an anomaly in space, especially for small university class CubeSats, that we can track those things and determine their orbits, even though we can't communicate with them. And so, or be able to determine their position from like Air Force resources. And so we've been developing some LED-based optical payloads. So you can see a picture in the bottom right, so the second from the right photo well, so that's my research, but so you can see me basically playing around with some of the payloads that we developed, and we've tested them on high altitude balloon launches. So just wanted to put that out there as a cool little tidbit of the year. But kind of moving forwards, so actually before we talk about MC9, I'll let Paul talk about TBEX.
Okay. So yeah, as I mentioned before, TBEX is currently in orbit right now, and so it uses 3 different transmitters at 150, 400, and 1066 megahertz, and it uses these to send signals through the upper atmosphere. And using this phase differences they measure on the ground, we can then figure out properties of the upper atmosphere. And so the properties we're actually specifically interested in are plasma bubbles. There's something that isn't extremely well understood, the way the full characterization and understanding of why they occur in the places they do and how they grow and change. And so by measuring them, we can characterize their size and their evolution in time, which we're very interested in. And the reason this is a kind of important research is because plasma bubbles have been implicated in as errors for why GPSs are less accurate, and they can also cause, because plasma bubbles are a different density, they will bend radio signals. And when they bend those radio signals, you can lose satellite coverage, or communications can not be as great, or GPSs can be less accurate. And so if we can figure out a correction to those plasma bubbles, we can then probably fix a lot of those sources of error. TBEX is kind of one of the most complicated CubeSats that we have ever done as a lab. It's actually the highest power CubeSat, and so there's a lot more systems to it. It has full 3-axis attitude determination. It has a fairly high powered payload because it has those 3 different transmitters, and so it's quite a bit to operate. But we're always learning how to do it better, and learning how to get more science out of the spacecraft.
Yeah, and also one thing we should probably add is that this mission, it's called the Tandem Beacon Experiment, but that's mainly because it's 2 satellites, which adds an extra layer of complexity to the mission. So it's not like you're just operating one satellite throughout the entire mission. We had to design, build, test, and operate 2 satellites through the whole mission. So you can actually see that satellite on the right, and then some of the images here are the middle one is us deploying from the SpaceX Falcon Heavy STP-2 mission in the summer of 2019. And then you can see a little screenshot of our operations computers tracking some of our satellites, which Paul gets to see a lot of. So moving forwards from TBEX, so our lab's always trying to find new missions to work on, and sometimes we're working on multiple missions at once. And so one of the really interesting things about this past year was that we were working on 3 flight missions at the same time. So we were working on a payload mission, so not necessarily a full spacecraft, but a payload mission, and then 2 full flight vehicles. So that was TBEX and then this MC9 Michigan CubeSat 9 mission that's flying the Mario payload. And so MC9 is going to fly hopefully in May 2021, so next year, on a Northrop Grumman commercial resupply mission to the ISS and deploy from there. But that's none of that has been kind of set yet, and unfortunately, COVID-19 issues may set that back quite a bit. But the main mission overall is research collaboration between NASA JPL, NASA Langley Research Center, and another lab in the aerospace department, which is AIMS. So they are a structures lab that's working on these things called MFCs, which are macro fiber composites, which are a piezoelectric material. And so I don't know if you guys can see my mouse, but up here, can you see my mouse, Paul? Just because everyone else is muted.
I do not see your mouse.
Okay.
Oh, no, now I do. Never mind.
So this is the Mario payload. If you can see my mouse, it's in the top right corner. And it's basically a test to figure out if we can use MFCs in space and raise their TRL, because they've never been used in a space environment in the way we want to use them. And so they can be used as precision electric actuators. They can be used as structural vibrators, and then they can also be used as structural health sensing monitors. And so you can actually build your structure out of MFCs, and if anything were to happen to it in space remotely when you don't have humans that can inspect it, you can actually detect any sorts of changes in your vehicle, whether it be a strain, whether it be a nanoparticle hitting the structure and actually creating a hole, and anything else kind of like that you can think of. And so this main mission, the reason why we're flying is we want to test the long-term duration performance of these MFCs. And so we've built up our engineering development unit, or EDU, which you can see in the image on the far right, and then the bottom left image of two of our lab members putting it together for some tests in the spring of this past year. And so then we're also working on some potential secondary payloads to fly along with the Mario payload. So as I was mentioning earlier, that the LED research we can potentially fly on an open solar panel position and work that into the spacecraft, or we can fly some intra-satellite wireless communication. So a challenge that the Mighty team was mentioning just before this was that they might run into some design challenges being able to communicate with parts of their spacecraft without wires. And so you can do that with radios, and we're trying to experiment with Wi-Fi inside our satellite, which is hopefully going to be a cool and useful experiment for the future. And beyond that, little, I guess, recruiting plug is that we are actively searching for students to help us kind of take over some of the work of some graduating members and push this spacecraft into space, and hopefully have anybody that wants to be part of it be a part of it. But Paul's going to talk about some of our operations research.
Okay, yeah. So operations is something that we do every single day to talk to our spacecraft, find out how healthy they are, and a number of other things. So one of the tools that we use a lot is something called SatNogs. And SatNogs is it's a global kind of network of ground stations operated by us, but then also a lot of other people. And so if we all can kind of put in a little bit of ground station resources, and then we can all pull out a little bit, we can actually get a lot more coverage for our satellites. And so this helps a lot with actually kind of finding out what's happening with satellites, getting data down, because now you can have downlinks all around the planet, even if you don't have yourself ground stations all around the planet. So in the bottom left-hand picture, you can see a picture of our antenna, which is on the roof of the FXB. And so it's kind of a cool thing, because you gotta run big RF cables all the way up there, and there's this big hole in the roof kind of in our lab. And apparently it's like a $20,000 hole in the roof, because it's a special hole. But it's really cool that we can have kind of that hardware right in the building with us. And then on the bottom right is Raspberry Pi, and so that's all it takes to run a single SatNog station. And so actually Justin set up a SatNog station for us in Ann Arbor, which allows us then to schedule all kinds of passes and listening observations all around the planet, which is super helpful. And then we can use our ground station to upload commands and tell the spacecraft what to do, schedule science operations, and we're always looking for more operators. It's something that's perennially short-staffed. So if anyone likes talking to spacecraft, I guess I'm starting to do plugs now too. Yeah.
Yeah. But yeah, it should be mentioned that you know, anybody on the call right now, if anybody here is interested in setting up a radio station in their home, at school, wherever you are, could even be something you do remotely, and just drop a station somewhere. You can set up a Raspberry Pi. We figured out that we can leverage the SatMogs network just this year to do some of our science operations. So this was something that was just brand new to us. But something that we figured out that literally anybody can do, and something that we're actually working with some high schools and elementary middle schools in Detroit to actually have them learn how to use some of these Raspberry Pi features and set up satellite ground stations in Detroit, which is pretty neat. But something you can do too. And Paul, you want to go ahead and explain this one?
So this is a dashboard we use for graphics. So we try to have one of these dashboards for all of our satellites in orbit. And so this is kind of just a macro view of all of the data the spacecraft is getting us. And this is kind of, this is a Grafana display board. And so it's kind of a really nice way of visualizing data, but you can also actually create like alarms for things. So if you want to, you can use your data then to kind of create an operational regime that you want your satellite to stay in. And if it believes that, you can add alarms, you can notifications, all kinds of things like that. And so that way, even if you don't, you don't have to dig through all the data all the time. You can kind of see it nicely plotted and really kind of get the intelligence out of it and what the important things you should be looking at as an operator, and engineer, and scientist. So for example, some of these are fairly straightforward data measures, like the magnetometer readings from different magnetometers on different parts of the spacecraft. But we also, like a lot of the temperatures, you can learn a lot of interesting things about how the components kind of, each time it's going through a orbit, it's going to be thermal cycling. And so from temperatures, you can sometimes figure out interesting structural effects. Something that we often pay a lot of attention to is obviously the temperatures, because we don't want anything to melt. We don't want batteries to get too hot or too cold. And so those are really important. The other one that I always end up looking at is the reset count, because each time satellite.
Yeah, Paul, we only have a couple minutes left, so I'm gonna. Well, okay. If anyone's interested in the data, we can chat about it in the room.
Sounds good.
But just moving forwards kind of quickly through some of the next slides, just because we are running out of time. MXL does do a lot of educational work too with students in the AERO department and other departments as well, if anyone's interested. So this year we were able to put up a high altitude global balloon module. So basically a circuit board with a radio on it with some science sensors that we could send up and float around the world and circumnavigate a few times, which is something a few people in the ham radio community have done. We basically went through a full design, build, test, fly cycle in the course of a semester for the lab, which is now a piece of hardware that we get to use. And then I guess the most exciting thing that our lab's done the past year was we were a big part of the MARCO mission, so the Mars Cube 1, which was the NASA JPL fly-along mission with InSight. And so MARCO was responsible for relaying critical data during the landing of InSight. And it was a giant precedent for small space vehicles, and in being the first mission to go to interplanetary space and leave Earth, or leave Earth's sphere of influence. And so we designed the computing and power systems for MARCO. Andy Klesch, who is the chief engineer, was an MXL alum. And you can see a photo in the middle of us. He brought the MARCO demonstration unit to our lab, and we all got to learn about it with him. On the right, you can see a photo that MARCO actually took of Mars. So that's pretty neat, and some of the things that we've helped enable. But in summary, we're a really small research lab of about 20 or less students at any given time, and we're just trying to make the biggest impacts we can in the small space vehicle world. But we are looking for motivated students to help us in the future. But thank you for listening to our talk, and we'd be happy to answer any of the questions about any of the stuff we've done this past year or even previous, or anything you guys are curious about.
Great. Thank you, Justin and Paul.